okay. Can you hear me?
Yes, sir.
Okay. Okay, sorry, I got late. The meeting was supposed to end at, I had a meeting at 5:30. I was definitely sure it'll end at 7, but it didn't even end at 7:50. So, no, I had it at 6. It started at 6. Okay, very sorry about that. Okay, so see, I think yesterday I got some email saying that it was they want an elaboration on what I did. So I will actually kind of uh, go a little bit slower, and I will explain also the intuition behind what we are doing. So I also made one small error yesterday, so I will kind of correct that and ensure that you get what is going on. Okay, so again, as I said, all the intuition comes from the classical problem, and I'll do a little bit more stronger connection this time. So recall the problem. So you have x and y, and you have a distribution pxy, and what you want to do is something like this. So you are getting x at one place, and what you can simply do is to generate a y according to py given x. So you generate this y and you send it out to Bob, and then Bob, just displays that y, and clearly this x comma y is going to look pxy. There is no doubt in this. What our protocol is something like this. Now, so I will kind of explain this once again. So you have a total size of set 2 power n h of y. Okay, you have one ball which is of size 2 power n h of y given x. Now we know one point, right? So suppose I pick 2 power n I of x colon y points in xn, then we know that they will be disjoint, right? So the most important thing here is 2 power n I of x colon y minus some small number eta, right? If I pick so many points in xn, then the conditional typical sets will be disjoint. I will make one statement without proof, is that suppose I pick 2 power n I of x colon y plus eta. Suppose I pick so many points in xn. Then I claim that these conditional typical sets, one thing you can see is that they will intersect. But you can say something more. They will actually cover the space. They will cover the entire space. What do I mean by that? They will cover the space of t delta n y. So in other words, so if I have xn of 1, xn of, so let me call this m, I have m. So if I look at the conditional typical sets of these fellows, so if I do a union over m, then I claim, I don't claim, but it is intuitive to see that this will cover the entire y space. Otherwise, you could fit something more, right, in some sense. So if you pick so many points, they will be disjoint and they will just kind of not completely cover the space, but the moment you start to pick more, that is, if you go above this magic number I of x colon y, they will cover the entire space. Okay, let us do one thing. Let us pick, so let's just choose 2 power n times h of y given x minus, this minus is important, eta number of bins. Okay, so I'm picking 2 power n h of y given x minus eta. So I'm picking a little bit smaller than any conditional typical set size. The number of bins I'm choosing is exponentially smaller than the number of points in a conditional typical set. Okay, so number of bins is smaller than any conditional typical set. And how, okay, so now what I do, I take the yn sequences. So I pick each yn sequence, that is typical yn, and I will randomly put into so many bins. Okay, so I have bin 1, bin 2, all the way until bin 2 power n I of x colon, sorry, I h of x y given x minus eta, exponentially smaller. See, this is exponentially smaller than the conditional typical set. So as n becomes large, the number of bins is significantly smaller than any conditional typical set. So you think you have 100 points in your conditional typical set, and the number of bins is only 3. As n becomes large, even a small exponent will kind of will show that there is a huge number of bins. The number of bins is much lower than the number of conditional typical elements in any ball. Now, what you do when you pick the points in your t delta n y, right? That is your unconditional typical set, this whole set. Okay, when you pick this and you randomly put it into these many bins, okay, so you're essentially each ball is of size, I mean the entire size to let's say the total typical set size is say 1 million, and each conditional typical set is of size 100, and you have 3 bins, and I mean 3 is looks very small, but maybe you can say maybe 30 bins, and you just randomly assign for every sequence a bin index. Okay, the question is, what happens to a particular conditional typical set or any conditional typical set? So the construction is something like this, right? You have, this is your bin. So each column is a bin. Okay, so bin 1, this is the last bin, and this bin is m, which is 2 power n times h of y given x minus eta. And each fellow size, each bin, if you randomly pick, there is no reason that they will all coalesce in one bin, right? Because you're picking an yn, and you're just randomly throwing into a bin. Picking another yn, just randomly throwing into a bin, right? And so there is no reason for one bin to get more aggregated. As n becomes large, you will see a uniform distribution. So what will be the size of any bin? Well, you're picking all your typical elements and you're putting them into bins. So this will be the size of any one bin in some sense. So this is going to be 2 power n I of x colon y plus eta. Okay, So now what you do, the what has happened in some sense is, see, I took one conditional typical set and I asked the question, will you find a representative in every bin? And because the number of bins is exponentially smaller than the number of elements in the conditional typical set, every bin has to have at least one conditional typical set, a conditional typical element from a conditional typical set, right? Now this should be true for any conditional typical set. So if you take a blue conditional typical set, or you take a red conditional typical set, or you take a purple conditional typical set, you will find in every bin there will be these guys. Okay. So what has happened is your conditional typical set, every conditional typical set has got completely distributed across the bins. They've kind of got shared across the bins. Now, what is nature doing, right? Nature, you can think of nature as picking an xn. She'll first pick an xn. And from that, she's going to look at that conditional typical set and she will pick something uniformly from that conditional typical set. And that's what nature is doing. So, so in other words, if you are given, so suppose you are given a blue xn. So let's say, these are the conditional typical set. So there is a blue xn, there is a purple xn, there is a red xn, and say there is a green xn. Okay. Now, if whenever you see the green xn, you pick among the green sequences uniformly at random, and you give that to Bob, and Bob, just displays that sequence, then xn and yn will appear as though nature picked them according to product pxy. Okay. So somehow you should randomize on the choice inside the conditional typicals. Somehow you should randomize. So when you get the green xn, somehow you should randomize here. So when you get the red xn, you should somehow randomize here. When you get the blue xn, you should somehow randomize in the blue sphere, and so on, right? And this construction will enable you to do that. What you do is the following. You ask for, so nature will give you an xn, and nature, this is not this nature, there's some other, so there are two sources of randomness. One source of randomness is the pxy source of the px source of randomness. Then there is some random bin index that you're getting. Okay, let's call this bin index, or in computer science, this is usually called as public coins, public random coins. So random, but public coins. So it's indeed random, but it is known to both Alice and Bob. So there's some public randomness that is completely independent of the xn. It doesn't depend on the xn at all. That index is used to choose your bin. Okay, so you have magically partitioned your entire yn space so that every bin has representative from every conditional typical set. That's the key. So every bin has a representative from every conditional typical set. So we know that if I choose 2 power n I of x colon y minus eta number of guys, they will have disjoint, disjoint conditional typical sets. But if I choose plus, and if I choose 2 power n h of y given x number of them, then I will be covering the entire space. So somehow this whole space is covered and partitioned. So this public coins is used to index the bin. So in other words, what you are doing, you have this huge yn space, and you are these blue points are there all over here, kind of. Okay, these are the blue points. And then, okay, maybe this is the okay, no, this is not the right picture. So if I take one bin, right? If I look at one bin, you are seeing points from each ball coming into that bin. Okay, so if you look at where the bin is, if you kind of look at the points in a bin, I will mark it with an X. The points in a bin are like this. The points in another bin are like this. So you pick your any xn you pick, its conditional typical set will intersect with any bin. That's the key. So you get a public index that gives you the bin index. So public index will give you the public coins will give you the bin index. And what Alice will do is, in that bin, she will find a few sequences that are typical with that xn. So in this, there is this red, and then there is this blue, and then there is this, green, and then there is this purple. And she will find one sequence, a few number of sequences that are typical with that xn. And she will give the index of that sequence out to Bob in that bin. The bin index is given to Bob. Okay. So Bob only needs what is the index inside that bin. For that, she needs 2 power n I of, so there are so many sequences in one bin, right? Remember the arithmetic. The number of bins is lesser than the size of a conditional typical set. So in some sense, the conditional typical set has to get spread out in every bin. So the number of sequences in a bin is so much. So if she uses so many indices, so if she uses I of x colon y plus eta number of bits, she can index the sequence she's looking at. That sequence has been chosen typical with the xn. She gives that, and Bob will just, display that sequence. He's got the bin index, he's got the index in the bin, and he will display that. And you can show that this protocol is almost very close to what nature is doing. So in other words, you can show that this protocol, if I implement this protocol, remember there is randomness. Where is the randomness? The xn is random. And furthermore, if there are multiple red sequences, suppose Alice has got a red sequence. Okay, suppose Alice has got a red sequence. And there are many red conditional typical sequences with that xn in a bin. She should choose them uniformly at random, just like simulating nature. She should just uniformly choose them at random, and she should throw that index out to Bob, and Bob will just pull that out, and then it look as though it is xy. Okay. Now, how does one do this? So that's where this measurement compression and all that will come. So just kind of bear with me now. I'll explain this measurement compression. So consider a bin. Okay, I'm going to write it in black. So consider a particular bin. I'm looking at a particular bin. So this is, I'll call it K. K is the public coin. The public coin index is the bin. Alice has observed a blue xn. Okay. What she has to do, she has to pick one among these sequences that is conditionally typical with xn, and she should give that index. Okay. Now, one way to do it is, okay, choose you just kind of just identify all the conditional typical sequences with xn, and you pick them. One of them you pick uniformly at random. There's another more like a systematic way to do it, and I will explain that. See, think of the following, right? Alice has observed x, and she's trying to estimate y. Okay, so you're trying to read the mind of nature, right? And what would nature have given? What would nature have given if I permitted nature, herself to pick y? That's what you're trying to simulate at Bob's end. So you also better kind of do that. What would you do? So you would do kind of, so you have a list of yn sequences, right? One approach is you conditionally typical, you pick one of them uniformly, pick one of the conditional typical sequences uniformly at random. I'll give you a slightly more systematic way to do it. So think of you are observing xn and you're trying to estimate nature's yn, which is coming according to pxy. So you're observing xn and nature has some yn in mind, and that x and y are distributed according to pxy. There's something called a map rule. Okay? So you have yn of, let's say, 1. So I'll put a k index because there is a k here. So 1 comma k, yn of 2 comma k, yn of, let's say, m comma k, capital M comma k. So this is the kth bin. Your public coins have indexed the bin k, and you have to choose one sequence among this, that is that nature would have chosen. Suppose nature had done this. Okay. So what you should do, you should pick an index m, right? And I should also pick it randomly. So essentially what I should do, I should give a distribution of that random index m given my observation is xn. This is what I should do. If my observation is xn, I'm going to pick the index little m with a particular distribution. What I'll do, I will pick like this, p, so x given y of n, xn given yn of m comma k. I'll explain this. See, the idea is the following. If you observe x and you're trying to estimate y, there is something called a map rule, maximum a posteriori probability rule. So you want to minimize the probability of error in choosing your y. Okay, so nature has some y in mind. You are given the x and you want to figure out what nature's y is. It turns out there is a rule to minimize your probability of error. And that rule is you choose that x, you choose that y which maximizes px given y. Okay, so you're given this, you look for, search in all those y's, what will maximize px given y, and you choose that y. Okay, this is what is called map rule. So you do r max y belonging to y. Okay, I will change this rule only a little bit to essentially have the same effect. What I will do is I will choose a y according to the following rule: x given y of xn. So I have received this. I want to give you a distribution of m. That is, how do I choose little m? I choose it like this: yn of m, the probability that I will choose the index m given Alice observes xn is given by the following. So I have a list of yns. This is my list of yns. Well, I should have put a k here, m comma k, because I fixed my index. Okay, so I have yn of 1, yn of 2, all the way. I'm ignoring the k index, yn of capital M. I observed an xn. I will compute this probability distribution. It's a distribution on 1 to, on the indices 1, 2 to capital M, right? It's a distribution on the indices 1 to capital M. I will choose little m with this probability. The ratio, compute this probability, then just normalize it. I will pick m according to this distribution. It turns out, see, if you see here clearly, right, those x and yns that are jointly typical will have a large value, and those that are not typical will have a small value. So essentially, this distribution is kind of emphasizing the conditional typical elements in that list. So whichever yn is conditionally typical with that xn, that will have a higher probability of you picking. And if there are many conditional typical elements, they'll all be getting kind of uniform, and the others will be almost not getting anything. So essentially, this rule is pretty much implementing that. but it's doing it with a kind of a slightly more formalized way. Okay, so this, it turns out, happens to be a good rule. So what you do, you just randomly partition all your yn sequences, and when you get an xn, you choose that m index based on that rule, and you give that index to Bob, and Bob will display that yn sequence. This whole protocol turns out to be simulating the distribution pxy very faithfully. Okay, now I will explain the quantum problem. If you have any kind of questions, just ask me now, and I will make the transition from here to quantum, and I will show you that the measurement is exactly an analogous of this formula. So if you have any question, just kind of stop me and ask me.
So like you may end up picking some y which is not even conditionally typical with respect to that xn.
That is happens, yes, it is in theory possible, but as n goes large, right? So let me explain. So as n goes large, right, px given y, n of xn comma yn of m comma k, right? If so let's study this under two cases. So two cases. So yn xn and yn of m comma k, this is typical and this is not typical. In this case, this kind of goes to around h of x given y. And in this case, when they're not typical, then remember the following. When xn is not typical, even if I sum over all yn of, if I sum over all xn, right, not typical, then this is very small. So that means every term here is really very small. So essentially, if I kind of look at so if I kind of plot the, if I put the bin now horizontally, so these are my yn. So this is my yn of 1, this is my yn of capital M, and I fix an xn. Then if I plot this x given y n of xn given yn of m, then when it is conditionally typical, it will have a huge mass, and otherwise it will have a very small mass. So there will be some of them conditionally typical guys that will have huge mass, and the rest will be very small. So the probability that you pick something that is not conditionally typical, yes, is there, but in the overall analysis, it kind of washes off.
Okay.
Yeah.
So why can't Alice do the following? Like she has this bin with her.
Yeah.
And then she can basically just brute force compute all the things which are not jointly typical with xn and throw them out, and then do uniform picking on the remaining things.
Yeah, that also you can do. That also works.
Okay.
So it turns out that analysis is what Wild has done in some sense. I mean, the Wild analysis in his paper is essentially what it translates to what you are saying. That is, you only put it on conditional typical elements. I mean, I'm translating it into the quantum world. You will see that come actually, but that also can be done. That also works. It is just that the analysis gets very, very, very tedious. Just the analysis, but as it's pretty much works.
So is he doing that by like conjugating by the typical subspace thing?
Yeah,
because he keeps doing that like very often.
So see, he not conjugating. He is actually quoting it. So he's quoting the measurements with the conditional typical elements. If you observe, so you go and look at his construction of his measurement. I'll actually come to that. He is quoting it with the conditional typical elements. So he's only going to choose conditional typical outcomes. Outcomes that are typical. And
yeah, like by quoting, he's like conjugating by the projector, right? The subspace projector.
Yeah, Yeah, he's actually doing that. Yeah, and you can see his analysis, he takes few pages to just prove it's a POVM, if you observe.
Ah, fine. Okay.
Even Winter is doing the same thing. And I'll tell you why they do that. I'll tell you what is the motivation they do that, and I'll tell you how, why I would do something slightly different. Okay, is this clear? Okay, now I will explain why the quantum problem is exactly analogous to this problem. See, what happened in the classical problem? You had X, right? The natural protocol is you just generate a Y according to Py given X. You generate this Y and you send it, right? Now, the measurement problem is exactly the same. Think of your X as a rho. So nature prepares a particle, rho. So remember, the rho is just a description of the particle. The actual description is the pure state. Okay? Your measurement is like, unfortunately, I'm using this lambda x. It's unfortunate, but lambda x is exactly like your py given x. See, what is lambda x? Lambda x is a measurement. So lambda x is a bunch of operators that sum to the identity, right? Now, just like I can throw any px to this p, I can throw any px to py given x and get a distribution py. Just like that, I can throw any particle rho to a measurement lambda x. Okay, I'll call this lambda. I'll call this lambda x. I can throw it to a measurement lambda x, and I will get a distribution. What is that distribution? Trace rho lambda x, x belonging to x. This is my distribution. So think of this lambda x as though it is your py given x. Okay, it's just like your py given x. So given you give me a row, it will induce a distribution on the outcome set. That distribution is given by this. This is analogous to py. So what you would do, if you were doing the natural, the basic, the naive protocol, you would take your particle rho, right? You see your particle, you apply your measurement lambda x, you're going to get a random variable x. This is going to be distributed according to trace rho lambda x. So this is like, just analogous, you're getting a distribution px. You're getting a sample from a distribution px. You apply py given x, and you put out a y, you send it out. So this x tilde is exactly like that. Now, what we are doing, we instead of doing this, right, we will get some message m, we will do some processing, and we will somehow get a yn out, right? And what is this measurement m? What is this message m? You do this binning, right? You do this binning of your yn sequences, right? You kind of all your yn sequences. Okay, you bin them into bins, and you get an xn. You choose inside bin index is given by nature, and you choose a yn according to this px given y of xn given yn of m comma k divided by summation px given y. You do something like this. You sum over I. The k is fixed by k is given by nature uniformly at random. So if you fix your xn, the k is getting randomly picked. So you're sampling the conditional typical set of xn. Okay. So you pick this m according to this, you send it out to Bob, and Bob is going to pull that yn out, right? So we will do exactly the same. So rho is kind of like your px. Lambda x is like your py given x. Sorry, py given x. Okay, so unfortunately, you're going to get the probability the outcome is little x. Outcome is little x is trace row lambda x. Okay, what is our rule? This px given y, right? What is px given y? Px given y is pxy by px by py, right? This is by your base rule. So it's pxy divided by py. Let's kind of do exactly the counterpart of this, pxy divided by py. What is py? Py is your trace row lambda x. I told you, unfortunately, this x and y are flipped. Okay, the same thing with wild also, but you'll have to put up with it. So what is px? So what is px? So I'll just kind of do the mapping. Px is like your row. Py given x is your lambda x. Py is the distribution trace row lambda x. This is the distribution on the outcome space that you see. Okay. Now let's see what is px given y. Px given y is pxy divided by py. So what is this? This is px times py given x divided by py. Okay. Now let me substitute the quantum analogs of this. Okay. So denominator py, this is trace row lambda y. What is px? Px is your row. What is py given x? This is your lambda y given x. Sorry, lambda x. Right? The only thing that happens in quantum is you're going to have a root row on the left and a root row on the right. That's really exactly our measurement. So what we will do exactly this kind of a table. We partition the yn sequences, right? Similarly, we will partition the space of all outcomes xn. We'll partition all outcomes. Remember, the x is like y, because you're seeing x is like your y. So just like we partition the yn space into bins, we will partition the outcomes into bins, and we will design a measurement. So what is happening? See the way it's working in the classical world. In the classical world, you get a bin index from the public coin. The public coin will give you a bin index. What do? You go inside that bin and you choose one of them uniformly. I mean, not one of them uniformly at random, but you choose one of them based on this rule. So what you are doing, you are in some sense making a measurement on xn, and you are getting one of these outcomes. So that means every bin corresponds to a measurement, and the outcomes of that measurement are a subsampling of the entire space of your outcomes. That's exactly what is going on. So what is that measurement? That measurement will be exactly this one. So kind of this should give you some intuition of what the measurement is. Otherwise, it's very hard for you to kind of understand what's going on. Okay, now having told all this, let me just pause for you to maybe see this, and then I'll continue. How many of you were lost? If you're lost, you lift up your hand with this analogy. I mean, I have not yet told you the measurement, but I'll tell you the measurement. Okay. Seem to be okay. Okay, let's go ahead. So I'll also do the part that I did a little bit fast yesterday. I'll just kind of go through a little slowly. So recall. So we want, so what is the left-hand side of this thing? It is IR tensor trace A tensor IY, that is I'm keeping, actually I don't know why you call it IY, it's called IX. So I'm keeping my register, I'm tracing out my particle, and I'm keeping my reference. Composed with IR tensor E lambda. So it is all tensor N, okay? So I'm operating on P omega. So this is what it is. What is omega? Omega is row tensor n. I will also do the following. Gamma u, eu. I'll do the derivation just a little bit once again. And then I'll go to the.
Hello.
Yeah.
Sorry, I just had a question in the previous part, slightly previous part.
Yeah.
This you said rho is the same thing as P of Px, right?
Yeah.
So, like, if we do the n repetitions bit, is it like rho sub xn would be the same as pxn?
Rho
Rho
tensor n.
tensor.
Rho tensor n is similar to pxn. So just like you, so when a particle is prepared in state rho tensor n, it is analogous to saying that you are given n samples of a random variable, each IID px.
Okay.
And
Each according to the marginal, which is px.
huh?
Each according to the marginal distribution, which is px.
Yeah. So your first x1 is according to px. Once it is generated, you don't look at it at all. You generate another according to px and so on, and you get n samples. That is analogous to the state rho tensor n.
Okay. And then the py given x is same thing as lambda x, because can you explain that bit?
Yeah. See, the lambda x, right? What it is doing, it is giving you an observable. Okay, so that lambda x is like you have a row. So you have a row, you're making a measurement. And for, okay, I mean, I wish I could call this, this is the reason why I wouldn't want to call it y. Okay, so for the moment, let's just take it as lambda y. What lambda y is doing is it is inducing a distribution on the outcome space y based on your row. What is the distribution it is inducing? It is inducing the distribution trace row lambda y belonging to y. So this is similar to, see, you have, so fixing a measurement is like fixing a box py given x. So there is a box that takes as input x, and that will throw out a sample py given x according to this distribution. So this is the distribution. The x is fixed. So if you give it y to this box, it will throw out a y based on this distribution. So now, if you happen to choose your x according to the distribution px, the distribution of the output that you will see is going to be py, because the probability that you will see x is px of x. Given that you see y, it is going to be py given x or y given x, and you could have got any x, so the probability of getting y would be py of y. So if I chose my input with the distribution px, my output will come out with distribution py. That's exactly like what it is here. If you give me a density operator rho, that's kind of corresponding your px, then I will give you an outcome that is distributed according to py. So this trace, this quantity is like py. This is like your conditioning box.
Oh, I see. Okay.
And exactly the same problem, because in the classical problem, the naive scheme, you get x, you would just pull out py given x according to y given x, and you throw y out. If you don't do any measurement compression, you get rho. You apply the unfortunately it's lambda x. You apply lambda x as is. You get a sample x. You put it out to Bob. I send it out to Bob, and this x and this rho will be faithful as though Bob did the measurement. Why not? Because essentially you've given him what you saw. Is that okay?
Yeah.
Yeah. Okay. Okay, cool. So let me go ahead. So I was here. So I will explain the measurement simulation protocol and then kind of go through it. So, okay, so omega is rho tensor n. Just do this little bit carefully. So rho tensor n. This is so rho has a spectral decomposition. Gamma u, EU, EU. Okay, so omega is UN. So gamma U1, gamma U2, gamma UN, EU1. I'll bring in some notation here. That's why I introduced this. So EUN, this is essentially EU1, EUN. I will also bring in some notation. Gamma UN is essentially gamma U1, gamma U2, product, gamma UN. Gammas are numbers, okay, real numbers, positive numbers that add identity. So summation gamma U is 1. As the eigenvalues of rho. Okay. I could also sometimes just say gamma underscore U, or I could also just say E underscore U. Okay. So I'm looking at a purification of omega. So purification, so I will let phi omega U root gamma U. So you know what I mean, right? So U is essentially U1 through UN, and gamma U is gamma U1, gamma U2, gamma UN. So this is a product. Okay, this is a tensor product. That's a product of real numbers. Let me know if you want slightly less number of Greek alphabets. So E, U bar. Okay, so no, I'll do some. Yeah, sorry. Yeah, so this is a purification of omega, because if I mean straightforward, but so phi omega is essentially U bar gamma U bar root EU bar EU bar EU. I hope you are getting what I'm doing. This is essentially a big product. This is a big bra vector. This is a big ket vector, I mean bra. And this is a big bra and this is a big ket. Okay, and I'm doing a dot product. And this will essentially give me U gamma U root. So it will be 1. So okay, so now let me tell you. So theta 1, I call theta 1 as the outcome of the first application. So IR tensor E lambda operated on phi omega. Okay, and theta 2 is IR trace out the particle and keep the register as is on theta 1. So theta 1 is your first, after the first operation, theta 2 is the second operation. What is lambda? Lambda is a big measurement. Lambda x1 tensor lambda x2 all the way tensor lambda xn. X1 through xn are all elements in xn. So I'm just, it's like a just independent measurements on multiple copies of the state. That's all it is. You get the first register, second register, third register, and nth register. Okay, so So I'm okay. So what am I doing? I'm doing IR tensor E lambda on. I'm going to write the state. I'll first time I'll write it slightly bigger. So U1 through UN, U1 hat to UN hat, root gamma U1, gamma UN, gamma UN hat, gamma UN hat. Okay. EU1, EUN, EU1 hat, EUN hat. This is just the first in the reference space, tensor. EU1, EUN, EU1 hat, EUN hat. Okay, so I'm applying, and this is my theta1 first state, just doing one by one. Okay, so what is E lambda? Remember E lambda. E lambda on S is summation root lambda xn S root lambda xn tensor xn xn. Okay, the state gets on the left with the root lambda on the left and the right, and I get the register sitting outside. That's my E lambda. So now my E lambda applies on the second, on the tail, right? And there's an IR on the left. So what does it give? So let's go. So I have an xn summation, a un summation, and a u hat n summation. So xn, un, u hat n. So I'll say gamma un because the product, gamma u hat n. So just put an underline just to indicate it's a big element. The first fellow is as is, un, u hat n tensor. Now the lambda xn will get stuck to the left and the right. So root lambda xn eun eu hat n root lambda xn tensor xn xn. Okay. This is your theta1. I can't do anything more with it. So theta1 as a reference space, has a particle space, and a register space. Okay. So this is your theta1. So let me write this down. So this is your theta1. Next step, I am applying IR trace A IXN, the particles, the register is left as is theta1. So what is this? So everything is the same except the ket bra becomes the bracket. So this is the ket bra, it becomes the bracket, that's all. So xn un u hat n, okay, root gamma un gamma u hat n eun. The first, I'm not tracing out the first class register, the reference space, it's as is. Tensor, when I trace out the particle space, I'm going to get e u hat n, okay, root lambda xn eun tensor xn xn. Okay, so well, I should not have a tensor here because this has become a scalar. Okay, so let me write that and put a red cross so you know it is not there. It is not. So now I can what I will do, I will also do one more thing. So I will just copy the whole thing and just write it as paste. I'm going to remove the root. So the root is gone, it's just one term. Okay. Next step. So xn un u hat n. Okay. I will do the following. Gamma un eun, the scalar, right? I can this scalar is very free flowing. This scalar is also not very free flowing. So I'm going to get that scalar in the middle. Okay. So eu hat n lambda xn eun. Write the and the rest is as is. So this black is as is. Okay. U hat n, and I put the root gamma u hat n on the right. Okay. So this free flowing scalar, this free flowing scalar, this free flowing scalar, and this I've been kind of displaced. Tensor xn. Okay. Recall gamma u. If I operate rho on EU spectral decomposition, this is gamma u EU, right? So root rho EU is root gamma u EU. That's the definition. So I can say root omega EU n is root gamma un, the same, whatever u is there, the same u guys is here. Okay, so what am I saying? I'm actually saying this. Operated on EU1 tensor EU2 tensor EUN with a root if you want. This is root gamma U1 EU1 tensor root gamma U2 EU2 tensor all the way until the root gamma UN EUN. So this is what we have written as root gamma UN, because the scalars are free flowing. You can pull all the products to the left, and then you can write the kets together. This is EUN, and so essentially it is root gamma UN EUN. That's really what so I can use that idea. I can use that step and go from here to here. So I have xn as is the first summation, un u hat n root omega eun eu hat n lambda xn un eu hat n root omega. So I will zoom out and show you what I'm now. So this I have put as root omega eun. This I have put as bra u hat n root omega. Okay, and this guy in the middle I've kept it as is. Okay, so now a small just a little bit just inner product algebra. So you can show that A S B is B S transpose A. Actually, it's not just this. There is some there is some B bar and all that going on. So I'll give you a reference for more details on this. It's not a big deal. Essentially, I can flip the order of this scale. I mean, make it complex conjugate. Okay. So I'll give you details about this, but let's not. It's a lot of just proving standard stuff. So root omega. So what I'll do is I'll flip this guy, okay, to what I really want it to look like. So the problem is there is a ket EUN and a bra EU bar n. I want ket bra EUN to fish out an identity and send it out. So lambda xn transpose E U hat n E U hat n root omega tensor xn xn. Okay, so this is, so now I can, this becomes the identity, this becomes the identity, or at least the projector on the omega space on which it, left side guy is sitting. So I'll get xn root omega lambda xn transpose root omega tensor xn xn. So this is the reference register. Okay. Now, so this is the left hand side, and now we will follow the analogy. So it's I'll follow the analogy, and I will now. So let's go back and kind of get an idea of what we have to do. So I told you there is this kind of this connection. So what have I done? So again, maybe I'll state this one, so that now the whole protocol should be clear. See, natural thing is you get X, you do the measurement. I mean, I'm talking in measurement terms now, but it's just you pull out a Y according to Py given X, or rather you do a measurement, and that measurement is this measurement, Py given X measurement. You pull out Y and you send it to Bob. That was your naive strategy. But now you do something else, right? So the quantum naive strategy is exactly the same. You get a row, you apply lambda x on it, you get an x. Unfortunately, it's x, it's not y, and you give that to Bob. That's a naive strategy. Now, the more sophisticated strategy, where you are able to see, you're able to simulate x and y identically without having to send h of y number of bits, right? Here, you don't want to send trace lambda x row number of bits. You want to somehow reduce and still make x and y look as though you had got it from the measurement, right? Just like you're simulating Py given x, now you're trying to simulate this, but without doing it, right? That's what you're doing even in the protocol, in the new classical protocol. What is your protocol? You kind of partition your entire yn space, right? And you do a measurement only inside the bin. So you ask some third-party nature to give both Alice and Bob some common random bits. You use those common random bits to look into a bin. Okay, that bin tomorrow will be different, day after tomorrow will be different, yesterday was different, and so on. That bin is completely independent. You can just look at the same xn, but that bin is randomly going. Okay, you use that bin index, and you make a measurement only for that bin index. So you design a different measurement. That measurement is the following measurement. So if you get the bin index k, you will pull out m according to the distribution px given y of xn given yn of k comma m. So your k is fixed coming from the bin index, the public coins. You pull m according to this. I think I flipped the M and the K. Previously, I used to keep the K at the right. So I equal to 1 through the total number of bin indices. Okay, total of bin indices. So you compute this distribution and you pick the index M according to this distribution, and that is now this is the measurement you are making. You have changed your measurement. If you were doing the previous thing, right? So if you were seeing, suppose you saw xn, big xn, you would just do the measurement px given y of py given x of this given xn. This is what you would be doing. And whichever yn, I mean, you don't need to do n things, but you would be doing n if you want to kind of. Now you are doing a different measurement, and each bin has a different distribution. Different distribution for each bin, for each xn that you see a different distribution on the bins, right? So similarly, so you can look at this as though you are partitioning your outcome space yn. These are all the outcomes you would have got. You're partitioning them into bins, and you are somehow making a measurement inside each bin. So you're only each when you fix a bin, you're only getting outcomes in that bin, and somehow you are able to do it as though it is exactly the same. We're going to do exactly the same. So we have this outcome space xn. What is the typical set according to which typical set do you partition? You partition the typical set py, right? What is py corresponding to? Py is corresponding to trace row lambda x. So you consider the distribution on x given by trace row lambda x. This is the distribution on x. Consider the typical set. So, unfortunately it is x, but it should be y. Consider the typical set according to this distribution. So previously you considered the typical set according to the py distribution, and you partition them into bins. You do exactly the same thing. You take the typical set according to this distribution. You partition it into bins. Okay, sorry. You partition it into bins. So what will you get? You will get so many. So I'm going to. So I will have a bin index because it's public coin, right? I'm using the word k. Okay. And the number of such bins will be 2 power n c bins. C for common randomness. C for public coins. Okay. So that will be the total number of bins. In each bin, there will be 2 power n r sequences. Okay. Clearly, R plus C, all the typical sequences should come. See, remember, if you do, you take row tensor n, and you make the measurement lambda, that is the big lambda xn. What is the most likely outcome? The most likely outcome are only going to be those sequences that are typical with respect to this distribution, because your outcome is distributed according to trace row lambda x. So if you, I mean, what is happening? Nature is just picking n of them according to trace row lambda x. Obviously, it has to be typical. So you take all the typical sequences in this and you partition it like this. And each thing, now you have to design a measurement. Okay, you have to design a measurement. See, the key point is the following, right? Key point is the following. If I take row tensor n, okay, I take row tensor n, I pick one of the bin indices uniformly at random. Okay, so please understand this, is a very important point. I pick one of the bin indices uniformly at random. I do the measurement corresponding to that bin index. Okay. What is the state of the system post measurement? that state of the quantum system should be like this component. See, this is the state of the system, including the classical register and the reference post original measurement. Now, if I do a protocol, whatever protocol I do, so I do this protocol, I choose a random measurement, I build a bank of measurements or a bin of measurements. I choose one among these bin uniformly at random, and I do the measurement corresponding to that. I'll get a post measurement state. That post measurement state should look exactly like this, both the classical register and the quantum part. So the key point is somehow I should simulate this post measurement quantum state also, but by not doing the original measurement. That is the key point. See, if I do a different measurement, the post measurement quantum state will go to something else. I have no control over it. Now, how do I ensure that when I uniformly randomize over these measurements, the post measurement quantum state is exactly like in here? Okay, so that is the key, and this should kind of give you some clue. What is my measurement? So my measurement, I will kind of mimic this. Okay, so I will mimic that. So what is my kth measurement? Suppose I get the bin index k. Okay, what is my kth measurement? So my measurement, kth measurement is theta mk. So it has m out, it has 2 power nr outcomes. Okay, so just like the number of rows in that thing. So what is theta mk? So I tell you what is theta mk. Theta mk, so remember it is px given y divided by summation px given y, right? And I told you what is px given y. Px given y is p y given x times px divided by py. Okay, I'm just writing pxy divided by py. Pxy is py given x times px divided by py. I'll substitute the quantum counterparts to this. That's all I will do. Root omega is like root px. Lambda xn of m comma k. That's like your py given x. That's like your py given x of a yn of m comma k given xn. That's exactly like that. Root omega, that's your root px. So I've just split the px into a root px on the left and this root px on the right. Divided by, I have to divide by py. That's exactly trace omega lambda xn of m comma k. Okay. Now, that is my px given y. This is only my px given y. Now I have to sum over all px given y. Okay. That instead of I can't write a division. I do sk power minus half on the left and sk power half on the right. What is sk? Sk is exactly the summation. Okay, I am almost out of time. What time is it? I started at 7:35, right? Yeah, it's 8:50 now. Just do so m equal to 1 through. So you can see now why the measurement is what it is. Okay, so I'll continue from the next slide. So what I do? So I'm doing the kth measurement. The kth measurement is sk power minus half root omega lambda xn of m comma k root omega sk power minus half divided by trace omega lambda xn of m comma k. This is if m is in 2 power nr. Then I'll have to do a little bit of if they don't sum up to the identity, so this is I tensor n minus the projection on the space Sk. Okay, Pk, I'll call it Pk. So if m equal to, let's just say -1, some default index where Pk is the projector on the range space Sk. This is my measurement. Now, what am I doing? So I'm now going to, I'm going to analyze. Okay, I'll leave it for some questions if you have any thoughts or doubts or looking complex. And then I'll continue. Mostly I'll continue. I'll have one/2 more lectures and complete this. At most 2, but I'll complete this. Questions? Okay, no questions. Cool. I will stop recording and then I'll most likely I'll not teach tomorrow. Most likely I'll teach on Saturday and Sunday and complete the course. I mean, I'm only want to complete this paper and analysis. It's not that difficult. It's just actually 3 steps. But I have to convey the intuition of this measurement and entire protocol. So what we will do is, so we will pick theta k uniformly at random. I mean, that given by the public coins. I'll make the theta k measurement. The quantum state will go to some state. So if I now uniformly pick these outcomes, it should look like this. It should look like this yellow state. That's the idea. So not only the classical register should be simulated like that, but even the quantum state picked uniformly should be like that. That's really what we have to show. That's the hard part. Okay, there are no questions. I'll stop.